Good morning, everyone. My name is Gökhan Demirel, and I am a PhD student at the Karlsruhe Institute of Technology. Today, I will present our work, as you can see on the screen, impact and integration of mini-photovoltaic MPV systems on electric power distribution grids with paper ID 21. Now, let's outline our key sections. First, we discuss the background and motivation. Next, the problem formulation, followed by the implementation results and the conclusion. We will now move on to the background slide. The power system includes generation, transmission, and distribution. Figure 1 illustrates the European power system and its dynamics. We investigate the motivation behind the integration of distributed energy resources, such as photovoltaic and battery energy storage systems, at the distribution grid level. This shift from centralized to distributed generation leads to challenges in terms of predictability and control, particularly in terms of voltage regulation and safety. In addition, DERs can cause reverse power flow from the end user to the main grid. However, this will result in the terminal voltage exceeding the safety value, thus jeopardizing safety. Let us now turn to the specific issue of balcony power plants or mini-photovoltaic systems. With 250,000 systems and 100 megawatt capacities expected in Germany by 2024, these systems are significant. Regulatory change such as 800 watt peaks, limit of the VDE or European Grid Code, addresses voltage rise, voltage drops, and power losses. We use sensitivity analysis to explore these effects of MPVs on DERs. Now let's move on to the problem statement. Problem formulation 1. Our problem is active voltage control problem. Figure 3 on the right shows the voltage drop in a radial electrical distribution system. The voltage drop delta A, J, is equal to the voltage drop at the node I minus at the voltage node J, in a distribution system with the line impedance given by the following equation. When distributed energy resources such as PV, BESS, MPV, or combination of DERs inject active power into the grid, the right-hand terms become negative, reducing the grid load and increasing the terminal voltage. The DER inverter capacities generates reactive power in accordance with the grid code, ensuring that the voltage increase is compensated. Let's move on to the distribution grid and data setting. Now, problem formulation slide 2. The grid is divided into feeder control zones, each zone containing multiple DERs such as PV, BESS systems. DER owners share observation within these zones. We use SimBench and MPV bench profiles as the benchmark data set for the grid topology, load, and PV profiles. We add mini-PV systems with different characteristics such as penetration, concentration, and configurable power of the mini-PV inverter. We evaluate the impact of MPVs on grid dynamics. In the first implementation slide, we focus on implementing reactive power and voltage control for distributed energy resources. Traditionally, DSOs have managed voltage by reinforcing the grid with new lines or advanced transformers. Alternatively, DSOs can control reactive power remotely in accordance with local regulations or grid codes. DER systems use three main reactive power control modes: PU of U, V, or reactive power as a function of voltage, PU of V with deadband, PU of P, and a fixed cosinus phi. The regulatory framework is the grid code VDE. Figure 5 on the right hand side of the slide at the top shows the QU of Y with the deadband reactive power control methods for the DERs. Figure 6 on the bottom of the slide shows the implementation of these reactive power control methods within the system boundaries of DERs. Our system has two feedback loops. The first variable is the active power generated or target value of the DER unit or inverter. The second is the current measurement at the point of common coupling. DSO controls the respective reactive power control mode remotely depending on the method which is used. The desired reactive power is then fed into the grid. A new measurement serves as feedback. The mathematical description is presented in our paper. Let's move on to the second implementation slide. To improve efficiency, we consider two control strategies for PV, BESS, and combined PV BESS systems. First, decentralized control. Each DER unit makes its own decisions locally. Second, the distributed control. All DER units work together to make decisions. On the right, Table 1 provides an overview of specific DER control strategies. PV strategy 1 powers local consumption, exports residual power to the grid. BESS strategy 1 charge BESS to maximum from 6 am to 6 pm, discharge to minimum from 6 pm to 6 am. PV BESS strategy 1 charge BESS when local power is negative and discharge when negative. PV BESS strategy 2 operators manage zones, charge or discharge based on joint residual power. PV BESS strategy 3 uses day-night control periods to charge and discharge BESS. Now to the experimental settings before we start with the results. We conduct the experiments with the reactive power control methods Q of E, Q of P, fixed cosinus phi, and with decentralized and distributed grid control strategies. We use PV and load data from SimBench and MPV data from MPV bench applied to a 15-bus distribution grid as an example. We define our matrix first, average voltage magnitude, which should be within the range of 0.95 to 1.05. Second, the total grid loss. Next, average transformer loading, which must remain below 100%. And finally, the average line loading, which should also stay below 100%. On the right side of the slide, you can see a table summarizing the control strategies for DERs and the reactive power control methods used in our case studies. In the first case study, we use distributed control strategy 2 for DER systems with the reactive power control mode. The second case study uses the same control strategy 2 for DER systems with different reactive power control modes. The last case study uses decentralized and distributed control strategies, as well as a day-night controller with Q of P reactive power control. In the first case study, we analyzed the sensitivity of MPV integrations on the electric grid using distributed grid control with PV BESS strategy 3 and the Q of V reactive power control method. We observe a piecewise linear increase in grid loss, transformer load, and line load, with increasing beta or increasing penetration of the MPV. The average transformer load increases from 34% to 38%. The average line load increases from 39.5% to 32%. Our sensitivity analysis shows how MPV integration affects the grid based on the parameter values alpha, beta, gamma 1 and gamma 2. The analysis shows that as the MPV penetration and the solar cell power increase, the average voltage also increases. This is due to reactive power control, which counteracts the increased active power injection from MPV integration, resulting in higher inverter losses. Now to the second case study. In the second case study, we compared different reactive power control methods using distributed control strategy 2. We evaluate how each voltage control method performs. Figure 7 illustrates the reactive power generation and voltage fluctuation performance using different methods on a summer day. The solid blue line represents Q of V, the orange dashed line represents Q from P, green dashed line shows fixed cos phi, and the red dashed line indicates no control. Our results show that all methods maintain the voltage within the safety range even at 100% MPV concentration. The average voltage magnitude for Q of V is below that of the fixed cosinus phi, but above that of the cosinus phi. In the third case study, we evaluate decentralized and distributed grid control strategies using Q of V as the reactive power control mode for all combinations. The figure on the right shows how battery charge and discharge, how much charge they have, and how much energy is lost in the distribution lines for different strategies. The first column shows the decentralized grid control. A decentralized grid control is a straightforward approach that uses local PV power to charge batteries, provides electricity for local use only. The second column shows the distributed grid control. BS units will access PV power from the feeder control zone, allowing for faster charging. Based on the distributed manner, the demands in the feeder zones are supplied by storage. High solar power generation results in high average line loading, especially when BS units are charging and discharging. The distributed control system ensures faster and more efficient energy storage management compared to the decentralized approach. Now to the conclusion. We implemented according to the grid code. We analyzed both decentralized and distributed control strategies for DRs. Our sensitivity analysis shows that the MPV integration increases transformer and line load by up to 4% and 2.5% respectively. Reactive power control reduces the voltage deviation but increases the power loss by 9%. We also provide the balcony power plant dataset for the energy committee with associated metadata and is available on our GitHub repository. Our findings include the fact that the current grid code leads to high losses with an increasing number of decentralized energy generation plants in the distributed grid. These findings underlines the need to further optimize existing regulations and technologies in order to ensure sustainable and efficient energy distribution. This also includes advanced control methods for DRs such as reinforcement learning or other control techniques. Thank you for listening. If you have any question, please feel free to contact me. I wish you all the best in the conference.